Hey, welcome back. This is now 8.4 on trig subs. And sort of the reason why you would want to do a trig sub is it kind of unlocks square roots. Okay, so I'll just say in general, they get rid of square roots. Or it kind of, you can kind of think of it as it'll take something which may be raised to some fraction power. So you see in problem 1 to the right there, the denominator is raised to the 3/2 power. In order to kind of collapse that two-term binomial into just maybe one term and then get rid of that fraction altogether, you could use these trig subs. And anyways, they're kind of like, they kind of at first make the integral worse. So with a u sub, your ultimate goal is to kind of reduce the number of symbols in the integral. And it always usually, if you do it right, it'll collapse into an integral that's elementary, that you can just look up in a table. These problems kind of work a different path. You're temporarily making the variable more complicated, but the end results will usually be a trig integral, and then you'll be able to kind of use 8.3 methods to deal with it. But anyways, let's take a look under the hood, right? So I'll start with problem number 2 there in WebEx, or something similar to number 2, my version. We have this problem, square root of 4 minus x squared all over x dx. And of course, you kind of usually want to, in the real world, you would just be given this integral at random, and you would say, all right, so I would probably want to do maybe a 4 minus x squared, and then du is negative 2x dx, and then dx is negative du over 2x, that kind of idea. But you would fail miserably, right? So this would end up being, and you don't need to write this out, the square root of u all over x times negative du all over 2x. And then you see the x's aren't going to cancel out in any nice way. So you may have to do some other substitution on top. It just gets worse, okay? So instead of doing that, what you're going to do, believe it or not, is kind of make it a little bit more complicated at first. So I'm going to say, hey, let's make x instead equal to 2 sine theta. And what will happen is that the stuff in the radical, you'll be able to kind of collapse it and turn it into a single term. Okay, so in the process, I'm going to need some more information to get the job done. So if you change x, you're going to have to change the dx. So you can just take the derivative here, be 2 cosine theta d theta. And then for the end process of converting everything back in the terms of x, we will have to solve for theta and use triangles in order to do our final conversion. So I take the first equation there, that x, and first solve for sine theta is x over 2, and then take inverse sine on both sides. So sine inverse of sine of theta will just be theta. And on the other side, you have sine inverse of x over 2. And then we can rewrite anything with thetas in terms of x's using this triangle. So if you recall, sine, the output of the sine function is opposite over hypotenuse. So the input of this inverse sine function is going to be opposite over hypotenuse. So looking at that triangle, this side is the opposite, this side is hypotenuse, and then that third side, if you solve using Pythagorean theorem, you have a squared plus b squared, which is x squared, equals c squared, which is 4. So a squared will be 4 minus x squared, and then a will be square root of 4 minus x squared. Okay, so I just need that information to kind of do my job as an integral person. So, okay, finally now we can see the magic of this process. So I go to my square root, I'm replacing x with 2 sine theta. So x squared will be 4 sine squared theta. Downstairs, I'm replacing x with 2 sine theta. And then be careful, you still need to replace the dx. And our new expression for dx is 2 cosine theta d theta. Okay, so it's that radical portion that I'm saying is kind of why I would want to do this technique. So let's kind of, rather than having to rewrite the integral 1,000 times, let's just kind of zoom in on that portion. I could rewrite it as 4 times 1 minus sine squared. And if you've mastered all of the required trig identities that I listed in the trig video, you'll recall that 1 minus sine squared theta is cosine squared theta. So this thing will equal 4 cosine squared theta. And then the square root of 4 cosine squared theta is just 2 cosine theta. Okay, so I could, it gets rid of the square root. It turns this this binomial inside of a square root into just one nice function, the 2 cosine theta. And as promised, what you're kind of dealing with now is a trigonometric integral, okay, which hypothetically, if you mastered 8.3, you'll be able to do this. But honestly, you'll probably just be getting a lot of experience sort of in country, as they may say, here. Here you'll be getting the experience. So anyways, let's look at the constant. I'll have a 2 over 2 times 2, so, 2. In the numerator, if you want to multiply across here, you'll have cosine squared theta. In the denominator, you have sine theta. I can turn that cosine squared into terms of sine squared, just using our trig identities. It's the same as 1 minus sine squared all over sine. And then I can butterfly it. So you'll have 1 over sine theta minus sine squared over sine is the same as sine. 1 over sine, that is cosecant. And then both of those are elementary. Okay? So you may have to look up the cosecant, but it'll end up being negative 2 ln absolute value cosecant plus cotan. And then minus distributing the 2, you get 2 plus cosine theta. So the integral of sine is negative cosine, and then there's a negative in front of it. Okay, and then plus c. All right, so that's half the battle, just eliminating that square root portion, and then we're able to get this antiderivative in terms of thetas. Now for the last part, I need to use that triangle stuff. Okay, this final part of the box that I did all my work in. So all you need to do is remember, hypotenuse over adjacent, all of those kind of identities, right? So for instance, cosecant of theta is equal to 1 all over sine, so that's going to be your hypotenuse over opposite, right? And then your cotan is basically adjacent over opposite. Cosine, I'll need to know that one for the third term, for the second term there. Cosine is adjacent over hypotenuse. So you need to have all 6 of those main ones memorized. So looking then at the triangle, I have negative 2 ln absolute value cosecant is hypotenuse, so 2 all over opposite, which is x, plus cotan is adjacent, so that's the square root 4 minus x squared side, all over opposite, which again is x, and then plus 2, cosine is adjacent, which is the square root of 4 minus x squared, all over 2, and then plus c. And of course the 2's would cancel in that second term, but that's the idea, okay? Okay, so hopefully that gives you some motivation for why you'd want to do this. Historically, these integrals, or not historically, but I mean, in your life as an integral student, these are going to be the longest types of integrals. So expect to spend some time on this homework. Don't be hard on yourself if you're used to only taking so much time to do your homework, and now all of a sudden you have a bunch of you're in over your head almost, but these are harder problems. These are the hardest types of integrals you'll probably encounter, okay? for now. Anyways, there's three types of substitutions based on the form inside your radical or your cube root or whatever. So the types, if you see an a squared minus u squared inside some sort of root, so maybe like the 3/2 power, you're going to let u equal a sine theta. And it's just so things work out so you can replace them using those Pythagorean identities. So basically, we had the sine squared plus cosine squared is 1. But then if you divide everything by sine squared, you get 1 plus cosecant squared is, 1 plus cotan squared is cosecant squared. And then if you divide everything by cosine, you get tan squared plus 1 equals secant squared. So you're trying to produce an expression that's replaceable via these identities in that original expression where you have like the a squared minus u squared. Okay, so other ones you may have to use, if you see a plus there, you're going to be using a tan sub. And then if you see the variable portion first, like u squared minus a squared, guess what? You're going to do a secant sub. Okay, so u equals. There are different subs you could do, and if you had, if we had a year to do all of our work, we could explore that. But for now, just focus on these three, and that will make life a lot easier for everybody involved. Okay, great. So let's go back over to the homework and maybe look at some more examples. So let's look at now number 3. And we have maybe something similar. I don't know if this is exactly the same. X squared minus 25 all over x dx. Okay, so if you look at the form, the variable part comes first. So if this is equation 1, 2, and 3, it's not equation 1, because in equation 1 the a is considered to be the constant. Okay, and so the u is the variable. So here the u portion is the x, and that's what we want to kind of identify how we identify the form. So it's equation 3, long story short. And so we'll say our x in this case is going to be 5 secant theta. Okay. All right, so I like to get all my information first. I suggest you do the same. So get your dx, so you get 5 secant theta tan theta, d theta, get your theta, so dividing both sides by 5 and then taking secant inverse, we get x over 5. I honestly don't know how you would do this problem without having to do a triangle or something. I've seen people try to get away with that, and I'm kind of like, did you really do that? Or did you use a calculator? So I need to see your work, is long story short, so I know you're not just, So anyways, secant, what was secant as a ratio of sides of a right triangle? Well, secant is just 1 over cosine, so this must be hypotenuse over adjacent. The input to the secant function is hypotenuse over adjacent. So hypotenuse must be x, adjacent must be 5, and then if you use Pythagorean theorem, you'll get x squared minus 25. And usually you see that expression back in the integral, the square root of x minus 25. And as a matter of fact, if you wanted to, you can almost rewrite that entire integral just using the triangle. Right, so if you see it's the square root of x squared minus 25 over x. What is that? Well, that's just opposite over hypotenuse. That's your sine function. So it's really just sine of theta. The only trouble there is you still have to convert the dx, right? So it would then be times 5 secant theta tan theta d theta. But if you would rather, you can just do it brute force, kind of, so to speak, using the method I've outlined already. So not as quick, but you don't have to memorize as much. We will rewrite x squared as 25 secant squared theta, then minus 25, all over x, which would be 5 secant theta and then times dx, which is 5 secant theta tan theta d theta. Usually just to the side, I kind of simplify this thing. You factor out the 25, so you get secant squared theta minus 1. And then from I call these the Pythagorean identities up here. The identity we use is the third one then. So if you move the 1 over, that thing would equal tan squared, right? So you'd have the square root of 25 tan squared theta. And then you take the square root of that, and you get 5 tan theta, right? So this ultimately that equals the integral of 5 tan theta. Let's go ahead and remove these 5 secant thetas, and then times tan theta d theta. And things are looking nice. You can factor out the 5, and you just get tan squared theta d theta. To deal with tan squared, you got to convert it into 1 minus, well, you use these identities again. So it's secant squared minus 1, squared theta minus 1. And then we can integrate each of those just using, they're just elementary integrals. Right? So this will equal 5 times tan of theta minus theta plus c. And then we go to the triangle to convert back. Okay, so you'll have 5 times tan of theta is opposite x squared minus 25 over adjacent, which is 5. And then minus 5 times theta, which is secant inverse of x over 5, and then plus c. So unfortunately, when you have the theta, you're kind of stuck with dealing with the inverse function. And yeah, so there it is. Okay. And then simplify the 5 over 5 is 1, but that's the idea. Okay. Let's look at another example, right? So let's look at number 5. And number 5 is a bit different in particular because you don't really see that square root anywhere. So you kind of get trained to think that, oh, the trig subs are good for square roots, and then they have a problem like number 5 where there's no square root involved, and you're kind of thinking, what's going on here? So don't freak out over this. It's just business as usual, except there's no square root. Okay, so let's take a look at how it would operate. You have the integral of 6x squared all over 36 plus x squared squared, and then a dx. All right. So the form you have is the plus form. It's that equation number 2 there. So our u, which in this case is just the x position there, our x is going to be, you take the square root of 36 is 6, and then we're using the tan function for that form. Then get your dx. That'll be 6 secant squared theta d theta, and then solve for theta from the first original formula. Theta will be tan inverse of x over 6, and then you could set up your triangle. So theta, what do we have? Opposite over adjacent, and then the third side from Pythagorean theorem would be x squared plus 36. Okay, great. Now I can start doing all my substitutions. So I have the integral of 6 times 36 tan squared. If I just, x squared is 36 tan squared. Let me write that as 6 times 6 times 6 is 6 cubed tan squared theta. And then down below, I'll have 36 plus, well, another 36 tan squared theta. And then the dx, be careful, dx is now 6 times secant squared theta d theta. Okay. Right. So, whoops, I forgot the square right here. Okay, there it is. Okay, let me then simplify this expression. So it's the same as 36 times 1 plus tan squared theta squared. And then 1 plus tan squared, well, that's our secant. That's our friend secant squared. Okay, and then I got to square that. Please note 36 is the same as 6 squared. So if I square that, I'll get 6 to the 4th times secant to the 4th theta. So let's rewrite this stuff. There's 4 factors of 6 in the numerator, so 6 to the 4th tan squared theta, and then there's that extra 2 factors of secant d theta. And the denominator then, I have 6 to the 4th secant to the 4th theta. And you see, all right, that stuff cancels. 2 factors of secant will cancel, and I'll be left with tan squared theta all over secant squared theta d theta. So one transformation that you as a student should often do with these trig integrals is to just, if you don't see what your substitutions to be or what you need to do, turn everything in the terms of sines and cosines, and then hopefully there'll be some nice cancellations, and you can go from there. Okay, so that's my tip of the day. If you have some integral in foreign trig functions, convert all the foreign ones into cosines and sines. So for instance, tan squared, I'm going to rewrite as sine squared. Unfortunately, my pen decided to stop working as usual. There it is. Okay, tan squared is the same as sine squared over cosine squared. And then 1 over secant squared, if you take the reciprocal, 1 over secant we know is just cosine. So 1 over secant squared must be cosine squared. And there you see, ooh, that's a nice cancellation. Dave, good job. Now we have something a little more doable. Sine squared integral, you need to go to the half angle formulas or the power reduction formulas. 1 minus cosine double the angle 2 theta all over 2 d theta. And then you could butterfly that guy into 1/2 minus 1/2 cosine 2 theta d theta. And then you got 1/2 theta minus, if you do a u sub, there'll be another factor of 1/2. So you get 1/4 sine 2 theta plus your integration constant, and now we can start back subbing, kind of. Okay, so the back subbing on the theta is no big deal. That's just going to be your tan inverse. Okay, so you get tan inverse of x over 6. The troublemaker is that sine of 2 theta, and it's trouble because you cannot use the triangle because it has a different angle on it. So it would screw up all of the sides. Okay, so how do I deal with that? Well, that's that other formula I had you memorize from the trig section. Okay, so the trig integral section, if you zip back and look at all the formulas I had you memorize, the formula you need is right here. Okay? And this problem comes up enough that you need that memorized to pull off this transformation at the end. So again, sine of 2 theta is going to be 2 sine theta cosine theta. They sometimes call that the double angle formula, but I don't remember. It's been a while since I taught trig, so I don't remember off the top of my head. I apologize if that's not right. But once you get that, then you can go ahead and use a triangle to transform the sine theta and cosine theta in the terms of x. Okay, so I get 1/2 tan inverse of x over 6. And this is really as hard as it gets. That extra transformation is kind of not easy to always remember, but it's really as bad as it's ever going to get for you. That extra sort of step that you have to pull off. But sine of theta, opposite over hypotenuse, so that's going to be x all over the square root of 36 minus x squared. And then cosine is adjacent over hypotenuse, so I believe that was 6 all over the 36 minus x squared. And then, of course, try to simplify it a bit for me. So tan inverse of x over 6 minus 6 over 2 is 3x, and then the square roots would go away when you multiply, and that would be your answer. Okay, let's make this our quiz. Let me get a different version that you can try. Oh, and it gave me the exact same numbers. How helpful. It refuses to give me a different version. Well, I'll predict if I just put a 5 and a 25 in those spaces, we'll have the job done. So this will be the video quiz for this section. I put 5 up here. Please show work, don't just write the answer. The point is that you kind of duplicate my work and hopefully learn something at the same time. Okay, so we'll make that the video quiz. I'll pause the video. Oops, we want to make not the 36, but 25, right? We want this guy to be the same as the guy up top. I apologize. All right, let me pause the video real quick. Okay, so that should be quite similar to problem 5, but okay. Let's now kind of look at some other variations on this theme and see how they go. So let's try number 7. Okay, so wait a second, my 7 is a bit different. Oh, there it is. Okay. Right, so 7, I have 1 all over the integral of 1 all over x times the square root of 4x squared plus 25 dx. So up to this point, our u has always just been kind of the x, right? So if you look at the forms, it can be general functions of x, though, u squared minus a squared, u squared plus a squared. So in this case, x, it's not just u is x, right? So in this previous problems, u has always been x. In this problem, the u term is really 2x, right? Because you could rewrite this, and I wouldn't recommend doing this, but it's the square root of 2x, the u squared plus 25 dx, okay? All right, so it seems like that is kind of what's going on. So what we do is say, all right, I'm going to let 2x equal, in this case, 5 tan, and there's the plus symbol there, so it has to be 5 tan theta. And then for the dx, you can just divide both sides by 2, so you get 5 halves tan theta, and then dx will equal 5 halves secant squared theta d theta. Then I want my triangle, so theta will equal tan inverse of 2x over 5. Here's my triangle, so theta, right triangle, opposite over adjacent, and then this side will be from the Pythagorean theorem. And then we can go ahead and dump everything into our integral and go from there. So the integral of dx, let's just put it in the numerator. So we have 5 halves secant squared theta d theta all over x, which is 5 halves tan theta. And then we have the square root of 25 tan squared theta plus 25. Okay, let's deal with the square root portion. So that's going to be the square root of 25 times tan squared plus 1. And then, of course, that's just the square root of 25 secant squared theta, and that'll just be 5 secant theta. Okay. So the 5 halves are canceling. And the integral of secant squared theta all over now. There's a 5 floating about, so 5 secant theta tan theta d theta. Again, it's one of these trigonometric integrals, right? So I'm gonna factor out the 1/5 here. Then kind of the 1 factor of secant will divide out, so you get secant in the numerator. And then you have 1 over tan, which is the same as cotan. And let's, okay, so we'll have cotan. And then let's rewrite everything in terms of sines and cosines again. So secant is the same as 1. Well, wait, is that? No, that's not going to be one of our nice little. Okay, so let's just write everything in sines and cosines. So secant is 1 all over cosine, and then cotan is cosine. Oh yeah, and there's a nice cancellation there that you wouldn't see otherwise, right? So the cosines are gone. Goodbye, goodbye, and we're just dealing with 1/5 integral of 1 over sine, which is cosecant theta d theta, and then of course that will be 1/5 negative ln absolute value cosecant theta plus cotan theta plus c, and now I can use my triangle to get back home in terms of x, right? So it'd be negative 1/5 ln, absolute value. Cosecant is the same as 1 over sine, so it'd be hypotenuse over opposite. And then cotan would be adjacent over opposite. And then plus c, and then you're done. Some of these can be quite challenging towards the end here. Let me try one of these. Seems like number 9 was kind of nasty. Let me try number 9. I'm marking my notes that I did number 9. But anyways, let's take a look. So I got the square root of 1 minus x all over the square root of x, and then we add dx. So in my mind, it doesn't really have the form that we're kind of looking for, but you can kind of abuse it a little bit by rewriting x as the square root of x squared. And then maybe if we do a u sub for, or let the square root of x be u, maybe we can get a nice cancellation with that denominator or something like that. So let's see if that works. So the derivative of square root of x is 1 all over 2 square root x. You just do power rule. Dx, and then yeah, we're going to get a nice cancellation. Dx is 2 root x du. And so subbing in that in, we have the square root of 1 minus u squared, which is an arc sine, or rather a sine sub, all over square root of x, which is going to be canceling out by the 2 square root x du. So that would be gone, that would be gone. You factor out the 2, and you just have this nice 1 minus u squared du, which is a trig integral, if that's not clear. So how is that a trig integral? We're going to let u equal sine of theta, and then go from there, right? So I'll just set it up, and you could do the rest in your homework. Du will be cosine of theta, d theta. Theta will be sine inverse of u, and then your triangle, sine inverse is opposite over hypotenuse, and the third side would be 1 minus u squared. And you can almost kind of see where it's headed. Adjacent over hypotenuse would be cosine, so if you wanted to use the triangle to simplify a bit, you could. It looks like it's just going to be sine cosine, right? So sine theta from the du part, you're going to get a cosine, but it should be cosine squared, right? Okay, so let me not fool around. I'll just do it the old-fashioned way. So 1 minus u, that'll be sine squared theta, and then du. I guess I lied. I'm going to do this problem. Looks like I can't stop. All right. So anyways, 2 integral. This will be square root of cosine squared. Yeah, and then we're going to end up with cosine theta times cosine theta, which is cosine squared theta, d theta. And I'll leave it to you. I believe you can get the rest. You have to do some back subbing to get the final answer, but you can see what the answer is there. Number 10 is a little nasty. You got to complete the square. Same spiel with number 11. Number 12 and 13, you're actually evaluating. I'll look at my notes and see if any of these are worthy of my attention. Just 1 second. Let me pause. Okay, number 13. I mean, these are definitely annoying because you have to complete the square and then do a u sub, and then it's just really a lot. Number 13, though, is definitely annoying. So to get number 13 done, you need this one integral, which I didn't talk about yet. So let me just really quickly give you this integral before you get in over your head with that problem. To do the secant cube problem, I mean, it's one of those ones you can have memorized, but it's a by parts, and we like to show you how this works. So, you're looking for your u and your dv. It's not clear what you should do, but you know what the the integral of secant squared is, right? So if you let dv be secant squared and then your u be secant, you could at least do something. You know, you could at least apply this method. So anyways, the derivative of u is, of course, secant tan. And then the integral of secant squared, fortunately for us, we know that is just tan theta. Okay. All right. So u times v, secant theta, tan theta, and then minus the integral of v du. So we get tan squared theta secant theta d theta. And then the transformation we want to do here is on the tan squared portion. And it's not intuitive by any means. You would probably have to play around with it a bit to figure it out. So you're going to replace tan squared with secant squared minus 1. And then you're going to distribute that secant theta into that binomial. So you'll end up with secant theta tan theta minus the integral of secant cubed theta minus secant theta. But you want to split these into two different integrals. Okay, so let me do that. The first integral will be secant cubed theta d theta, and then distributing the negative, we get plus integral of secant theta d theta. And so why would I want to do that? It's because we've created a looping situation, right? So the original integral, just borrowing it from above, was the secant cubed theta d theta. And once you see another secant cubed theta rear its ugly head, you know we can just replace that integral with an I and then solve for the I, right? So we would have I equals secant theta tan theta minus I plus secant theta integral d theta, and then add the i's together. Then we know the integral of secant is just ln secant plus tan. And then you just divide by 2, and that's what the integral equals. So it's a lot like the integral of secant, but there's that extra secant tan and, of course, the constant of 1/2 about through it. But we need it for problem numero 13. In 13, they're asking for evaluating it first by changing the limits. No, first, don't change the limits. And the second, change the limits right off the bat. So I'll kind of also try to kill that bird. So anyways, number 13, we have the integral from 4 to the 6 of x squared all over the square root of x squared minus 9 dx. So this is a secant sub. So x will be 3 secant theta. And then you get your dx, which is 3 secant theta tan theta. And then get your theta. So theta will equal secant inverse of x over 3. And then we can get our triangle. So secant is 1 over cosine, so that would be hypotenuse over adjacent. And the third side would be x squared minus 9. Okay, so you can proceed as normal, and then at the end, just slap the limits, the 4 and the 6 back on, and then do your evaluation. Or you can transform the limits at the beginning. So part A is when you go all the way to the end and just put everything back in terms of x and evaluate. Part B, you're, rather than back subbing everything, and you wouldn't even necessarily need the triangle for part B. In part B, all you're doing is replacing the x limits with the following. So the top limit would be, in that case, 6 all over 3. So anyways, it would be secant inverse of 2, which doesn't seem like anything I'm familiar with. Did I screw that up? Yeah, 6 over 3, 2, secant inverse of 2, 1/2. Oh yeah, so that's equal to pi over, so secant again is 1 over cosine So cosine, that'd be pi over 3. And then the other theta would be secant inverse of 4 over 3. And yeah, I have no idea what that is. So you would just kind of have to leave it as secant inverse of 4/3 and then use it. I mean, that's optional if you want to go down that route. Sometimes it's a little quicker. You could try that on your own. But what I like to do is just integrate it as normal at the end, then I'll evaluate it on the antiderivative on the limits after everything's back subbed. Okay, so I'll do it, kind of try to do both at the same time, but we'll see how well that works. Okay, so anyways, I'm going to drop the limits at first. We have x squared, so it's 9 secant squared theta all over the square root of 9 secant squared theta minus 9, and then the dx 3 secant theta tan theta d theta. I forgot my d theta down here. Okay, this junk inside the root, we want to deal with that. So that's just square root of 9 times secant squared theta minus 1. That'll equal the square root of 9 times tan squared theta. And of course, that'll just be 3 tan squared theta. So we have 27 secant cubed theta tan theta d theta. Sorry, it's still in red. All over 3 tan squared theta. Let me go back to black. 27 by 3 is 9. And then we have the integral of secant cubed theta. The tan should have canceled out somehow. Sorry, let's make sure I got it. Secant tan. Oh, when you take the square root, you just, oh, I screwed up, sorry. It's that right there. It should just be tan. And then the tans will cancel, and you just got the secant squared, 9 secant squared d theta. And then you have to use my formula for secant cubed. That will just then equal 9. When you should distribute the 9 halves secant theta tan theta. And then is it plus or minus? So it's minus 9 halves ln of secant theta plus tan theta. And what they're saying is you can evaluate right now with the pi over 3 and the secant inverse of 4. So let me try to do it that way. So I have 9 halves. Then first I'm putting this pi over 3 in there. So secant of pi over 3, that's the same as 1 over cosine, which will be 2. And then times tan of pi over 3. What the heck is that? It'll be root 3. And then minus 9 halves ln of the same baloney. 2 plus root 3 in that case. And then minus, you have to go to the secant inverse of 4/3. So secant inverse of 4/3 is just going to be 4/3. And then tan of secant inverse of 4/3. So you can kind of work with a triangle again. Theta, secant is hypotenuse over adjacent. So this third side will be 16 minus 9. Which will be square root 7. Okay. So secant inverse of 4/3 is 4/3, and then tan of secant inverse of 4/3, you use the triangle, so that's going to be opposite square root 7 all over adjacent, and then minus 9 halves ln of the same business, right? So again, secant inverse of 4/3 will be 4/3, and then tan of secant inverse of 4/3 will just be the root 7 over 3. Okay, so that nasty beeswax is kind of what you see, hopefully, in our final answer there. Let's clean it up a bit. So I have 9 root 3. I could combine these two terms using rules of logarithms. Basically, the difference is a quotient. The difference of logs is the log of the quotient, so you'd have plus 9/2 times the ln of, let's see, I'm going to have to take the reciprocal, no, I'm going to have to, it's going to end up being 4 plus root 7 all over 3 times the 2 plus root 3, so that would be 6 plus 3 root 3, and then where are we? Minus 4 root 3 over 9. And then it seems like I can even combine the 81. What is 81 minus 4? 11, embarrassing myself here. 77, looks like 77 root 3 over 9. Plus this 9/2 ln, absolute value 4 plus root 7, all over 6 plus 3 root 3. Let's see if that's even close. Yeah, that's, well, one was root 7, Dave, not root 3. So you get tan of that. Tan is root 7 over 3. So this term right here should be a 7. Sorry about that. So there's no, I can't combine those two together, which is a bummer. It's a very sad day in math land. But anyways, that answer should be hopefully it. Let's take a look. 9 root 3. Must have screwed up the constants there somehow. Is the middle part even right? Yeah, the middle part looks right. Except I put a minus instead of a plus. Let me pause the video, I'll find the mistake, just one sec. Okay, yeah, so the biggest mistake, and this is why it's kind of helpful if you watch the whole video, is right here. In my original integral for secant cubed, it's actually a plus right there. So that's not a good thing. And then this will turn into a plus, so this will be a plus. This will be a plus. And I lost the constant right here, so that would be 9/2. All right, so what's going to happen is eventually that will turn into a minus, and then that last term, the 9 will cancel, and you just have 2 root 7, so minus 2 root 7. Okay, so that's, if you do this conversion with the theta, that gives you part B, but the same thing, the answer in part A. So let me erase that last bit of work and kind of go at it with the other method. Right, so in the other method, what you're doing is kind of forget about this and just convert everything back in the terms of x, right? So you get 9/2 using the triangle now. Secant is 1 over cosine, so you're going to get hypotenuse over adjacent times then the opposite over adjacent, and then plus 9/2 of the ln of the sum of those two things, x over 3 plus the square root of x squared minus 9 over 3. And let's see. No, let's evaluate. Righto. So in this case, we have 6 and 4, or go to the fourth 6. So we probably want to simplify a little bit first. So of course you have x, then square root of x squared minus 9 all over 2, and then plus 9/2 ln absolute value x plus the square root of x squared minus 9 over the common denominator of 3. Evaluate from 4 to 6. So this thing will be 6 times 36 minus 9 is going to be 27. So you have 6 times the square root of 27, which is going to be 3 root 3 over 2 plus 9/2 ln absolute value 6 plus, again, root 27, which will be 3 root 3. That will be all over 3 minus, plugging in 4 now, so you get 4 times 16 minus 9. 16 minus 9, that's where you see that root 7 like we had before, all over 2 plus 9/2 ln absolute value. Then it will be 4 plus root 7 all over 3. In case you're not picking up on what I'm doing with the logarithms, just it's to combine this term and this term, it's 9/2 ln absolute value of 6 plus 3 root 3 all over 3. And then minus the other one is minus 9/2 ln absolute value 4 plus root 7 all over 3. And then to combine those, the difference of logarithms is the logarithm of the quotient. Okay, so you can factor out the 9/2, and then you'll have ln of the absolute value of 6 plus 3 root 3 over 3 divided by the 4 plus root 7 over 3. Dividing is the same as multiplying by the reciprocal, so you have 3 all over 4 plus root 7. And then the 3's will divide out, and you'll be left with the following. So I'd have 9 root 3 plus 9/2 ln absolute value of 6 plus 3 root 3 all over 4 plus root 7, and then minus the 2 root 7, which is what we got previously. It was just a bit nastier because that one, the secant inverse of 4/3 is not kind of from a reference angle that we could just evaluate in our heads, right? But this is it. I know the answer, it says minus, but that would just take the reciprocal of what's inside the log, so you would get the same thing as what I got here. Right? So anyways, I hope you watched to the end there and you got the plus symbol. Let me just, I mean, obviously you have the quiz, you don't have to watch the rest, but let me just try number 11, because it seemed like that's a bit awkward if you've not seen it before. So if you need to, you can watch it. If not, hey, have fun. But let me do number 11 just for the completeness for everybody who may need it. So they're giving us the integral of x all over the square root of x squared minus 14x plus 45 dx. All right, so I need to complete the square in the denominator. So I have x all over square root of x squared minus 14x plus 14 over 2 squared, right? So it'd be 7 over 2 squared is 49, right? Sorry, 14 over 2 is 7, and then 7 squared is 49. Then you immediately subtract 49 and add the 45, that was already there. So I have the integral of x all over the square root of x minus 7 squared minus 4 dx. And then you're going to have to do a u sub on that x minus 7. And here it gets a bit sticky because that numerator isn't in terms of x minus 7, right? So I'm going to do a u sub on the x minus 7. My du will just be dx. But then in the numerator, I'm going to have to turn around and rewrite x as u plus 7 using that first equation. So I have the integral of u plus 7 all over the square root of u squared minus 4, and then du. Then, I mean, honestly, I don't even think you need to do, well, maybe you will on the second integral, but you can do a u sub or maybe some z sub on this. So I'll split it up into two fractions, right? So the first fraction is just a u sub integral. I don't need to do a trig sub. So in the first fraction, the first integral, I'll just say z is u squared minus 4, and then dz will be 2u du, and then du will be dz over 2u. The second integral kind of looks like an arc sine, but it's not. Arc sines are always like 4 minus u squared. It looks more like a secant. But if it was a secant, it would have a u out in front in that denominator. It'd be u, then the square root of u squared minus 4, and it's just not that. So you kind of are forced to do a trig sub. Okay, but anyways, you get rid of the first guy. So it'd be u all over z to the 1/2 times dz over 2u, and then plus this other thing. You can factor out the 7 if you want. On the second integral, then you're going to have to say, all right, let's let u equal 2 secant theta, and then du will be 2 secant theta, tan theta, d theta, and then your theta would be secant inverse of u all over 2, and then you're going to your triangle. So that would be hypotenuse over adjacent, and then the third side would be u squared minus 4 from the Pythagorean theorem. And then we have 1/2 integral of z to the negative 1/2 dz plus this other guy, what is it? U is 4 secant squared theta minus 4. Du will replace a 2 secant theta, tan theta, d theta. And then we're going to simplify that radical. This thing will be square root of 2 times secant squared minus 1. Of course, secant squared minus 1 is just your tan function. And of course, oops, I got a 4, not a 2. I'm jumping the gun there. And then that will be 2 tan theta for the denominator. So we have, we can factor out the 2 or just let it divide out eventually. Anyway, let's just put the 7 in front still. Then we have integral in the numerator, 2 secant theta, tan theta, d theta. In the denominator, we just have 2 tan theta. So this will be 1/2 z, doing power rule on it. Negative 1/2 plus 1 is positive 1/2 times 2. Plus the 2's cancel, the tans cancel, and then the integral of secant is just the ln of the absolute value of secant plus tan. So not too ugly, but annoying enough that I just wanted to do it for you. So anyways, back summing the z portion at least. So we have u squared minus 4, wasn't u squared minus 4? Yeah, to the 1/2. And then plus, now I have to back sub the secant theta and stuff. Ln of the absolute value secant is, using now the triangle, hypotenuse over adjacent, and then tan is opposite over adjacent. And now we want to back sub the u expression, which was originally x minus 7. Okay, so we end up with x minus 7 squared minus 4 to the 1/2 plus 7 ln absolute value x minus 7 over 2 plus the square root of x minus 7 squared minus 4 all over 2 absolute value plus your integration constant. Okay. Yeah, so that one's a bit nasty, but kind of just, it is what it is at the end of the day. You just have to get the integral done. As usual, I thank you for watching, and I'll see you in the next video.